Welcome everyone to lesson 3.9 of Precalculus, which is all about inverse trig functions. So let's get started. First and foremost, I want to recall our time when we were discussing solving right triangles and finding missing sides and angles of right triangles way back in geometry. So when we did that, we would set up an equation like this: sine of 37 degrees is equal to x over 5 for this triangle. And then for this triangle, we would set up sine of x degrees is equal to 4/5, and then we would take the inverse sine to find out what the x is. So what do those properties have? Are those functions? How can we define those as functions? So let's explore that. So the sine function is this S-shaped curve. It has the following properties. We know its domain is negative infinity to positive infinity, and its range, it oscillates between -1 and 1, right? Inverses, we've taken inverses before, mean that we're switching the inputs and the outputs. So if I graph the equation x is equal to sine y, I would essentially take all of these points and I would switch their inputs and their outputs. So I know that sine is an S-shaped curve, 0 at 0, it's 1 at pi over 2, 0 at pi, -1 at 3 pi over 2, 0 at 2 pi. And I could repeat the pattern backwards, and I get the beautiful S-shaped curve, which is now looking more like a piece of DNA. Oh, glitched out there, but glitched out there, but it's fine. We can see this, and it's beautiful. It's in its own right, but it's not a function. And it's not a function because if I draw a vertical line, that's not quite vertical, but you get the idea, it fails the vertical line test, which is the easiest way graphically to tell if something is a function or not. So this is clearly not a function. But that doesn't mean that we can't have an inverse. We've taken inverses of functions that, when you do switch the x and the y, aren't functions anymore, and we handled this by restricting the domain. So let's do this instead. Let's let the sine inverse function have a domain of -1 to 1, which is the range of sine, but instead of having a range of negative infinity to positive infinity, we restrict ourselves to the right side of the unit circle. So we're starting at negative pi over 2, and we have everything from pi over 2, negative pi over 2 to pi over 2. What does that look like graphically? Well, we can tell from up here that we are just snipping this part out. I don't know why it doesn't like that, but we're taking this part of the curve and we're snipping it out. So we're taking this part, and this part, and connecting them like so. That little tiny function is the inverse sine function. So again, we are restricting ourselves from being able to go around the circle, 1, all the way, and 2, an infinite number of times in either direction, to a quarter rotation above and a quarter rotation below 0. And if I look at it and I try to visualize y, right, I'm getting, because y is the y value of all these points, I'm getting a -1 here, I'm getting a +1 up here, so there's a +1 here, -1 here, and I'm getting everything in between in this one smooth curve. So that is why we're taking ourselves and restricting ourselves to negative pi over 2 to pi, because I get all of the values. I get the -1 to 1 all within a single smooth curve. So here's something else that's important to know. We can also call this inverse sine function the arc sine function. Why arc sine? Like, where does the arc come from, an arc sine? And I think it comes from a very beautiful place, which is the arc length formula. We learned before that arc length is equal to the angle in radians times the radius of the arc, right? But we define the unit circle to have a radius of 1. So for the unit circle, the arc length is equal to the angle in standard position, which means that since the sine inverse outputs the angle measure on the unit circle, and that is equivalent to the arc length formed from that specific angle, they are equivalent and therefore mean exactly the same thing. So if you see arc sine of theta, know that that is also sine inverse of theta. I personally personal preference, I actually like this one a little bit more. Usually I'm prone to trying to favor things that I don't have to write as much, but there's a reason why I don't like the -1 there, and we can talk about that if you want to. But I digress. Let's keep going. So that was arc sine. There's arc cosine and arc tangent as well, so let's have a go at those. Arc cosine's a little bit different. We're going to restrict cosine's domain to 0 to pi for the exact same reason. Remember that cosine is the x value of these points. So I get all of the x values from 0 to pi from 1 to -1 in one smooth curve. So we're using the top half of the unit circle, and that's a common theme with these inverse functions is we're only using half of the unit circle. So if I take this nice cosine curve, I'm keeping this part here to this part here. I'm taking this smooth curve and reflecting that along the line y equals x. So that means our arc cosine has a domain of -1 to 1, same as sine, but has a range that's slightly different, a range from 0 to pi. So if we take these values here, 1 is a 0, and pi is a -1. So we get this curve here. So again, it's a small little snippet, a quarter of a half of a period of cosine, and that's it. Tangent is similar but different. So tangent has a problem that we discussed last class, and that is vertical asymptotes. So it's actually quite nice to see that for tangent, it makes sense that we're only going to take one of these multitude of tangent curves. We're going to take the entire thing. And we can do that by using the same half as sine, from -pi/2 to pi/2, just not inclusive this time because that's where our asymptotes are. Which means that our domain is -infinity to positive infinity, but our range is only -pi/2 to pi/2. So what we're going to do actually is at pi/2 and -pi/2, we're going to put those asymptotes. Remember, when we take inverses, vertical asymptotes turn into horizontal ones, and we can actually plot some of these points and therefore get this curve here, which is kind of interesting. It's the only inverse of the three that goes on towards infinity, and that's kind of cool. And again, we can play around with this, and you ask any question you want, but that's kind of how the inverses work. Let's do something with that. We've been talking for a while. Let's actually do something, right? So here's a function, a sine function, and we have a restricted domain. Let's find the inverse of this, and then the domain and range of the inverse. So first and foremost, I am going to replace the f of x with an x, and the x with a y. And then we're going to solve it. So subtract 1 from both sides, divide by 2, so we get x minus 1 over 2 is equal to sine y, and then we take the inverse. So y is equal to arc sine, or inverse sine, of x minus 1 over 2. That's all fine and dandy. How do we graph it? Well, we know we're going to use these values, and we can also use 0. So we know that we have 3 real key points to use for the sine function. So I'm going to make an xy table. We're going to have -pi/2. We're going to have 0, and then we're going to have pi/2. And then sine of 0 is 0. 0 times 2 is 0, plus 1 is 1. Pi/2 up, so that would be 1. 1 times 2 is 2, plus 1 is 3. And then -pi/2 would be down. So -1 times 2 is -2, plus 1 is -1. And when we graph this, we're just going to switch what the x's and the y's are. So we don't have to make this more complicated than we need to. We know that at 1, we're going to have 0. At 3, we're going to have pi/2. And at -1, we're going to have -pi/2. So we're going to have this curve here. And that's it. That small little piece is all we have. So from this, it's kind of easy to tell what the domain and range are. The domain are the extreme values. So this -1 to 3 And we can have them, so they're inclusive. The range, well, they gave that to us. They already gave that to us here. They restrict the domain for us, which becomes the new range, so we're just going to steal that. Negative pi over 2 to pi over 2. Nope, inclusive. So hard bracket. Not too bad. Now, last but not least, let's evaluate some of these. So if I want to evaluate sine inverse of 1/2, what I'm going to do is I'm going to draw a triangle, specifically with the opposite side of 1 and the hypotenuse of 2. So if I draw that triangle, we have a theta here. This is 1, this is 2. That reminds me of that type of triangle. And so this is a 30, 60, 90 triangle. The smallest angle is across from the smallest side, which means that this is pi over 6. This one here, we're going to make this the opposite, and well, not the opposite, no. We're going to make this the adjacent and make this the hypotenuse. So the adjacent being negative means that we're going to the left. A little theta there. We have negative root 2. I'm tripping over my words here. And 2. That looks like to me a 45, 45, 90 triangle. And since we're going to the left, this is in quadrant 2, so it's 45 degrees more than 90. This is 135 degrees, or 3 pi over 4, because we're in pre-calc, we should be dealing with radians. And then last but not least is the tangent of root 3. Root 3 is just root 3 over 1, so this gives us the opposite and the adjacent. We're going to draw a triangle. Everything's positive, so we're in quadrant 1. Opposite is root 3, adjacent is 1. That kind of reminds me of a 30, 60, 90 triangle, which means middle side is across the middle angle. This is pi over 3. So not too bad, and we can solve them the exact same way we did before with triangles. We just have to remember what these triangles look like. Special triangles have special angles, and if you're asked something that isn't a special angle, you can always use a calculator for it, and we're going to practice some of that in class as well. So hopefully this wasn't too bad, and if you have any questions, make sure you ask them. Otherwise, I'll see you in the next lesson.